Hello, everybody. Welcome to the second workshop of today for fundamentals on-chain agents. We have Jakub from the Giza team with us today, who will be going over. Let me just quickly find him in the chat. There it is. Jakub will quickly with us. Apologies for the 1 minute delay. There were technical issues that we wanted to figure out, but all is good now. So we'll be kicking off in a bit. Welcome. Oh, hey, Jakub.
Hey, how's it going?
Cool. So everybody, as I said, today that's going to be the second workshop. For those of you that missed the previous one, don't worry about it. All of our workshops are being recorded, and you will be able to watch the recordings from the Hacker Pack, where we will be publishing the links. In the meantime, if for this workshop, if you also have questions, feel free to voice them and paste them in the questions tabs. In the questions tab, it's on the lower right side of your screen next to the chat one. Jakub will be answering them as we go along. So yeah, Jakub, if you're ready, feel free to take it away.
Okay, awesome. Let me share my screen and we can kick it off.
Perfect.
Okay, awesome. Okay, so first of all, can you see the screen now?
Yes.
Okay, cool. Great to have everyone here. I'm glad there's quite some interest in our work, and I think it's going to be a great hackathon. So today I wanted to give a workshop on the fundamentals of on-chain agents. So this is a bit more of a technical walkthrough of the entire agent workflow, and we're gonna have a live coding demo. My name is Jakub, and yeah, I'm a data scientist at Giza. Okay, so first, what we're gonna walk through. Oh, and by the way, if there are any questions as I'm speaking, please feel free to raise them either in chat or or in the questions section. I'll be trying to check both of them as I go. But I can also take some questions at the end after the entire presentation. So yeah. So what I wanted to talk about today is first a quick intro to Giza and ZKML, which we won't spend much time on because I know you guys probably already know pretty much everything about us from the previous workshops. But I also wanted to give an overview of the Giza agents, kind of from a technical perspective, but more on like a higher level, kind of like a conceptual technical overview. And then based on the example of our Uniswap V3 liquidity position rebalancing agent, kind of walk through how deploying an agent works in practice and how this entire process is. And finally, we'll have some time for the questions. Okay, so yeah, as I said, I will not spend too much time on us because you probably have a pretty good understanding of our work already. But the main gist of it is that Giza is a ZKML company. ZKML stands for Zero Knowledge Machine Learning. So what we're trying to do here is create cryptographic proofs of inference of machine learning models. So once you create your machine learning model, when you ask that model, when you feed this model new input data and ask it for inferences, what ZKML allows you to do is to create a cryptographic proof that says that this particular result of running this input data on this model that you have was achieved in a computationally correct way and was not tampered with at any step of the entire process. And we have a couple of components of our entire tech stack. One of them is the CLI, the command line tool that allows you to deploy models, deploy endpoints for inferences, create agents, and run those agents actions. Finally, also there's Actions SDK, which is a Python-based SDK, software development kit, that allows you to code the entire logic of the agents and use those Python scripts to trigger the agent interactions on-chain. And we also have Giza datasets, which is, you can think of it as just like a repository with machine learning optimized datasets curated for ML practitioners, with the idea that fetching on-chain data is oftentimes quite hard. They have to understand some cryptography, work with different RPCs or different technologies, and we want to streamline this process so we have one repository with lots of useful data sets for you to work with. Okay, so without further ado on us, I wanted to talk a bit about how we're thinking about the agents and how this entire architecture looks like at the moment, from the perspective of how this interaction of agent with the chain looks throughout its entire lifecycle. So first, you as a user, you create an agent, you deploy that agent to our platform. And that generally happens through the CLI. You can also use the Actions SDK for parts of that process, but yeah, generally you're going to be using our CLI tool for it. And what it does is what an agent deployment, which we're going to walk through later in this workshop, is it creates the agent instance in our platform, and then that agent can be used to run any action that you want on chain. So once you deploy the agent to Giza, you can also create a schedule that agent to run. You can trigger its actions manually, but you can also schedule it to run, let's say every minute, every hour, every day, whatever your use case demands. So once that scheduler decides it's time to run the agent, it fetches the data naturally, which will be needed as an input to your machine learning model. This can be either any external data source, like some sort of an API, like CoinGecko, maybe Dune Analytics, whatever you're comfortable using. But preferably it would be an on-chain blockchain data. And the main reason for that is that this way you're kind of putting more maximizing trust for your users, right? Like if the core data, if the input data to your machine learning model comes directly from chain, it minimizes the potential of someone really messing with the data to attack your application. So using on-chain data kind of minimizes that attack surface. So once the data is fetched, pre-processed, you can do whatever you want to do with this data inside of the agent. Once this is done, the agent sends a request to its API endpoint. So it sends the input data, and in the Giza platform, we're running the machine learning model, and we're also asking the model to generate the proof, which then gets verified. So once you run the model, you're generating the ZK proof, and then the proof verifier needs to verify the validity of that computation, of that machine learning prediction. And only once this verification is complete and the proof checks out, only then the model, the agent is ready to act and to further interact. So if at any step of that process something goes wrong and there's no verification of your inference, the agent will not act. And yeah, the main idea behind it is that you want to use machine learning on chain in a trustless way, right? If you have a cryptographic proof that this computation was done in a correct way, you can be pretty much certain that no one really tampered with it in any way. So you should be comfortable taking an action on that prediction. So once this model output is generated and the proof is verified, it sends the data back to the agent, and the agent can start doing all of the things it's designed to do, right? So in a DeFi application, it will probably execute some sort of a trading strategy. It can be, in our case, it will be Uniswap rebalancing. And once it goes through all of those steps and is ready to actually submit the transactions on chain, the agent also holds the private keys of the wallet that we wanted to use. And with that, it's able to actually interact on chain and finally submit the transactions to the chain. Are there any questions so far on that entire design? I see there was a question about the ape framework, which was already answered by Fran. But yeah, just to reiterate, so the ape framework is used within the agent. So yeah, first like taking care of the account that the agent is supposed to use. That's done through the ape framework. The on-chain interactions also happen through the ape framework. Of the interactions with different contracts. If it's, for example, fetching some data, that can also be achieved with the ape framework. Yeah, so it's primarily used within the agent scope.
And just to bring your attention to the questions tab, I think we got our first question. So for all the listeners and everyone that's watching, please use the questions tab. That's going to help Jakub to just quickly see your questions. Yeah.
Yeah, so the question is, does the verification of the agent happen off-chain or on-chain? And the answer is it happens off-chain. If you wanted to run this computation on-chain, it would be difficult, but it's technically possible. But practically, it would be extremely costly. Even if you wanted to use a very cheap L2, running an entire machine learning model inference on-chain would be prohibitively costly. So you would probably spend tens or hundreds of dollars to run a one single prediction, and then unless you're running a multi-billion hedge fund, it probably doesn't really make sense for you to do stuff like this. So the entire idea of what we're doing right now is that we want to give the machine learning intelligence to on-chain agents, but without having to compromise on that compute efficiency. So we want to still have the ability to perform that heavy computationally heavy operation of running a machine learning inference off-chain, but to have a cryptographic guarantee that can later be used on-chain. And if you want, you can design your smart contracts in such a way that they consume the proofs generated off-chain and verify them on-chain. That's also possible. It's not something that we've really been focusing on, but technically it's definitely possible. And I see the follow-up question, what is happening on-chain in the Uniswap V3 example? So yeah, in the Uniswap example, this particular agent that I'm going to show you today is rebalancing the LP positions, and that's what's happening on chain, right? The act of rebalancing the position, adjusting the bounds if the logic deems so, withdrawing or adding liquidity. That's what's happening on chain, but kind of the logic of how this should happen happens off chain, and this is based on that inference from an ML model. Is that clear, Satya? Does it make sense to you? Okay, cool. Yeah, so if there's any more questions about the Giza stack, please shoot them in the questions or the chat section. If not, I can move on to talking about Uniswap. So yeah, I would assume most of you are familiar with Uniswap, but just a quick recap for those who might not be that deep into DeFi. Uniswap is currently the biggest decentralized exchange in crypto. And what it allows you to do is to swap between two different tokens in a permissionless way and without having to interact with a centralized entity like a stock exchange or any other fintech application or a TradFi institution. All happens through the smart contracts deployed on Ethereum or any other chain that Uniswap is on. And the main innovation that Uniswap V3 introduced is the idea of ticks, and well, not the idea of ticks, but rather the usage of ticks to provide concentrated liquidity. And concentrated liquidity, and that's in the Uniswap case means that you can decide what's the price boundary within which you want your liquidity to be active. So in previous cases, when you were in Uniswap V1 or Uniswap V2, you could just provide the liquidity to, let's say, USDC ETH pair, and no matter what the price of USDC to ETH was, you would be earning fees on the liquidity that you provided to that pool. In Uniswap V3, this design is slightly altered in a way that you, as a liquidity provider, decide what price range you want your liquidity to be active in. And the reason for why it was designed this way is because if you can push your bounds very narrowly and close to the current price of the pool, you will be earning more fees, right? Because some of that liquidity will be outside of the current price, and all of the swaps are happening, on the within the current price, plus minus price impact of any given trade. So yeah, providing concentrated liquidity is generally more capital efficient, and as a liquidity provider, LP for short, you can earn more fees on your capital deployed. The caveat here is if you don't do it in a correct way, and for example, you assume that let's say the current price of Uniswap is of ETH is $3,740, and you provide the liquidity between 3,730 and 3,750. If the price migrates outside of the bounds that you've chosen, you are no longer earning any fees on your liquidity provided. Added on top of that, there's impermanent loss, which I will not really cover in this workshop, but because we could spend hours talking about it. But the core idea is that if you don't choose your liquidity bounds properly as an LP provider, you're likely to lose the money. But on the flip side, if you do it properly, you're likely to earn more in fees based on your capital provided than using full range like in Uniswap V2. So right, so like as an LP, you have this trade-off, right? Do I put wider bounds and risk earning less fees, but then don't have to worry that the price will deviate outside of my bounds? Or do I try to keep it very narrow, close to the current price, but take a risk that if I don't really keep track of what the price is doing constantly, at some point it will migrate outside of my bounds, and at that point I'm just losing money. It's a hard quantitative problem, and we can use machine learning to help with that. So this agent that I want to show now is doing exactly that. It's using volatility prediction to decide how wide the bounds should be. And if you want, you can follow the tutorial yourself with the source code on our GitHub. I can actually paste it in the chat as well. Copy link address, chat. Okay, it should be there. Okay, that's in the chat if anyone wants to follow. But yeah, with that, let me show my code editor, and we can walk through the flow. Okay, so the first thing before you start coding is you're gonna need to set up your environment, install all of the packages, set all of the environment variables. You will also need to configure your ape account. All of that is covered in the tutorial under this link that I sent. So yeah, fret not, it's all there. You can just follow the steps and it should work. But once you're done with the setup, first step is to create a model, right? If we go to this entire framework here, architecture, everything starts with the agent deployment, and in order to deploy an agent, you need some machine learning model that it will be running on. So the first step is to create an ML model. I will not really cover in depth how to create your machine learning model. In this script, I'm just using Yahoo Finance data for the Uni ETH pair, right? I have two different price data frames for Uni USD and ETH USD. I combine them to run the analysis on the Uni ETH pair. I train a simple neural net with PyTorch. And finally, I serialize it to ONNX. So ONNX is this file format that basically is common to multiple different machine learning frameworks. So you can be using PyTorch, you can use sklearn, you can use TensorFlow, Keras, whatever else you're familiar with and you're comfortable using. But all of them are kind of compatible with ONNX. So as an entry point to the entire Giza CLI, you're going to need an ONNX model. So once we train our PyTorch model, we export it to ONNX, and this is what this function is doing. I will run it to just so we see that everything is home. Okay, second. Okay, and what this file should do, it should train the model, give me some statistics on the performance of this model. Okay, in that case, it's pretty bad. So here I'm measuring the root mean squared error. It's quite a badly performing model, but it's just to show the idea of how to use the agent. And it serialized the model to torch volatility model.onnx, which I can now see in my directory, in my root directory. The next thing you're gonna need to do is to log into the Giza CLI. You generally do it with Giza users login, and it will prompt you for your login and password. I think I'm already logged in, but we can confirm it with the command Giza users me. Yes, should take a couple of seconds, but it should print my account details. Yeah, once this is done, we will want to create a Giza model. So a Giza model, you can think about it as kind of like a skeleton that holds all of the information about your model, including the actual weights to the neural network, or like the actual like model in any other format you have, but also it serves as an easy way to quickly iterate over different versions of the model. So like if you deploy a model and you see that, for example, it's not performing as you expected, and you have a suspicion why that is, you can retrain the model and deploy a new version under the same model. So you wouldn't really need to, like create a new model and then have tens or hundreds of different models running, but you can just have one model for a specific application and just go through iterate through different versions of it.
Just to quickly interrupt, Mahmoud is saying he cannot see what you're typing. So I don't know if
can someone else confirm if they have the same issues?
Can you try and do some?
Can you see?
I can see the console moving, but
yeah, I'm only showing the console now. Well, I mean, I'm showing more, but
he said the issue is on his end, so I think yeah.
Okay. Yeah. Okay. I think Cham can see it.
Cool. Just want to make sure.
Cool. Sorry about that, Mahmoud, but yeah, maybe you can refresh and maybe it's gonna work, hopefully. Okay, so back to us. The first step in the agent deployment process is creating a Giza model. So we will create it with the Giza models create command, and we can pass the name of our model and the description. The description can be much longer than that, but yeah, I'm just keeping it simple for the sake of the workshop. Okay, so it successfully created a new model in the Giza platform, and it gives us the ID of our model. We're going to need to save it because we will need it for the next steps. And the next step is transpiling the ONNX model into Cairo. So Cairo is the language used by developed by Starknet, more precisely for the Starknet chain. But yeah, it's a language common for people interacting with zero knowledge, working with zero knowledge proofs. Yeah, so what we need to do is to create a Cairo program out of our ONNX model, our machine learning model in ONNX. And the way to do it is with the Giza transpile method. And what you need to pass here as parameters is the model ID. So as you can see, I have the model ID 1782 here. I'm also passing it here. Generally, you will want to use Cairo framework unless you have a reason to use a different one. But this is up to you. Another thing you're passing it is the path to the model. So this is this model that we saved here, right? Torch underscore volatility model on NX. And finally, the output path. So where do we want the Giza CLI to save the transpiled Cairo version of the ML model? Let's run it. Shouldn't take too much time. But yeah, it's going to create a new version of this model. So if we were to, if we wanted to create, if we deployed this agent and see that, for example, it's not performing as good as we wanted to, and we want to retrain our model, we can deploy it with the new version, right? So we don't need to create a new model and then go through this entire process. We can just update the version with the new, in that case, weights of a neural network. Yeah, it shouldn't take long, but let's give it a second. Once this is done, we should see the Giza volatility model directory. And what it has is it contains the Cairo program of the model with different like weights and biases for each node in the neural net. In that case, of course, if you're using a different model, it will be slightly different. But yeah, if you're using a neural network, you will see something similar to this. So now the next step is to deploy an endpoint. So we need an endpoint to be able to run the inferences on. So think about it as like an API endpoint where you send your input data and you get back the inference, the prediction of your machine learning model. So we deploy an endpoint with Giza endpoints deploy command, and we also need to pass it the model ID, which in our case is 1782, and the version ID, which in this case is 1. Yeah, we're also going to need to give it a second, but it shouldn't, there shouldn't be any problems with that. And finally, once this is done, we will be ready to create a Giza agent. Yeah, let's wait for this to finish. Okay, I think we're fine. Yeah, it gives us the endpoint URL. You could probably use it to just outside of the Giza agents if you wanted to run HTTP requests against it, but I wouldn't really see a reason why you would want to do it. But yeah. Okay, and finally, well, not finally, but as next step, we can create the agent. So as you can see, when we created the endpoint, it gave us the endpoint ID. So when creating a Giza agent, you can either do it with the endpoint ID. In that case, I already have this endpoint deployed, so I'm going to use endpoint ID. But alternatively, you could pass it the model ID and the version ID as another way to keep track of what this agent, what model this agent should be using. And yeah, we can give a name and a description to this agent as well. Sorry, I think let's remove that. Yeah, that should be fine. Okay, and what this command will ask you to do is it will prompt you for which ape account you want to use. So remember at the beginning I told you that in the setup phase you're going to need to configure your ape account, and this is because the agent needs to have some EOA, some externally owned address that it can use to actually sign the transactions and interact on chain. So yeah, it's asking us which wallet should it use. In that case, I'm going to give it my development address, and yeah, we have successfully created an agent. Now with that, we can move to creating the core logic of what the agent is supposed to do, how it's supposed to act on the prediction, how it's supposed to fetch the data, how it's supposed to pre-process it, and finally how it's supposed to use that prediction to act on chain. So let me actually run this run the command that's going to run the agent and generate the prediction because it's going to take a while. So I want to run it first, and then as it's running and we're waiting for the output, I can walk you through the code of what the agent is doing. Yeah, so as you can see here, I'm just executing a simple Python script, right? I'm not interacting with the CLI anymore. I'm just executing my Python script that implements the agent logic, and in that case, I'm passing it some variables. I see there is a question. Okay, so the question is, can you explain the interaction between Giza ONNX model and the ape framework? So the life cycle on how the agent gets created and starts interacting with on-chain smart contracts on different chains. Okay, so the first part of this question is about the model and its interaction with the ape framework. So first, it's not really a Giza ONNX model. It's just ONNX is just an open source framework that's used by PyTorch, TensorFlow, a bunch of other machine learning frameworks. And it's just, it creates a computational graph. It just represents the given machine learning model as a computational graph. And with that computational graph representation, you can do a bunch of different things. In our case, we're turning that computational graph into a Cairo program. And this is what this Giza transpile command is responsible for. So once this is done, we are saving the Cairo program in our Giza platform. And with Ape Framework, Ape Framework is more used for interacting on chain and doing all of the blockchain related operations. So it doesn't necessarily interact with the ONNX model in any way, but you can use the Ape Framework to fetch the data from the blockchain that you will then use to feed into your machine learning model to get the inference based on. But you will also use the Ape Framework to create the agent, right? As we showed in this step. Yeah, and under the hood, Giza agent is using the Ape Framework to conduct all of its on-chain operations. Yeah, I don't know if that answers your question, or do you have some points that you would want me to clarify? Yeah, if any, please shoot them, and I can continue in the meantime. Okay, so we can go through the action agent itself. So first, I'm reading in my script, right, getting all of the imports, nothing interesting here. Fetching all of the environment variables that I'm going to need. And now with the Actions SDK from Giza Actions, I'm importing the task. And using Giza tasks, we can create the entire workflow of our machine learning application using those tasks. So like one task could be fetching the on-chain data. Another task could be pre-processing that data. Another one could be, for example, fetching some statistics from that data to direct the logic of how the agent should act. In my case, there's nothing really fancy going on here. My processing of the data is very simple and very, very naive. I don't interact with trying to get any data. I'm just hard coding those values for now for the sake of the workshop. And another task could be the creation of the agent. So this is more of an instantiation of the agent that you can then use in the Python program. It's separate from creating the agent through the CLI that we just walked through before. This is more like fetching this agent and creating a Python object out of this agent that we just created from the CLI so that we can use it to generate the predictions. Yeah, I have a task to run the inference and finally to verify this prediction. So basically this verification happens whenever I'm trying to access the predicted value. So in the final workflow, as you see, I'm going to first run the inference of the model, and I'm going to try to access this data. And this before I can access this data, the Giza platform will run first generate the proof, second verify this proof, and only once this proof is verified and it checks out, only then I will be able to access this data and continue the agent operations, right? So in that case, it's interacting with the smart contracts, and in most of the cases, it will be interacting with the smart contracts. But yeah, so what we're doing here is we are creating all of the objects that I'm going to need. I'm storing different contracts. So in order to interact, to create a new LP position or to change a position, I need to interact with the NFT manager deployed by Uniswap. So this is like an entry point to managing your LP positions, because those LP positions are represented as NFTs. I have 2 tokens that I'm going to want to interact with to deposit into my LP position. And then finally, I have a pool that I will want to deposit that liquidity into. I am instantiating the agent object with all of the appropriate parameters. So in that case, it's the model ID, the version ID, the chain that we want to use, contracts, and finally the account that we want the agent to use. We run the prediction, as I said before, and we're waiting for the verification of that prediction to happen. Once this is done, we are ready to interact with the smart contracts. So in my case, I am fetching all of the open liquidity positions, closing the existing ones, or like closing the particular one that the user wants to close. I'm calculating the parameters for the minting operation, right? So like you can't really, if you want to change the bounce in the Uniswap LP position, you can't really change the NFT. In that sense, you have to close the position, withdraw all of your tokens from that position, and then redeploy a new LP position, which will mint you a new NFT token. So this is why I'm first closing the position, withdrawing all of the liquidity, then giving the approvals for the NFT manager contract to spend our tokens, in that case ETH and Uni. I'm doing some simple conversion here, and yeah, calculating the tick range. So in Uniswap, when I was showing this graph, right, those are not really, like price values and the way we think about them. They're in what's called a Q notation. So, like this one current tick, which represents the current price, which is this 3,704 USDC for 1 ETH. And the Q notation is going to be something that completely doesn't make sense to it. It will be something like minus 2,745. Made up number, definitely. It's not that, but you get the point. So we need to have a conversion from this to from this Q notation representation into our the way we think about the prices, so that we can then run any statistics we want on it and decide what actually is what are the ticks that we want to provide the liquidity into based on our volatility prediction. And finally, calling the mint function on the NFT manager. And if everything goes well, you should see the transaction receipt, and you can check the transaction on-chain. And I think everything ran correctly. Yes. So maybe I will not go through all of the logs, but the more interesting things of it. So like first, those first transactions are probably closing of the existing positions and withdrawing all of the liquidity. We could open that link and see the actual transaction in a Sepolia scan. And finally, as the last step of the entire model, we created a new NFT position, and here's the transaction receipt of that position. We can probably also open it in Etherscan and confirm that everything worked as expected. Probably here. Yeah, so we see that the agent called the mint function and yeah, minted as a new NFT token that represents our NFT position. And in the production setting, if you want, you can schedule it to run, let's say, every hour, and this scheduling will be taken care of within the Giza platform. I see there's a few questions in the chat, so I will go through those right now.
Gonzalo is already answering once again,
Okay.
so helping a lot with the responses.
Okay, awesome. Thank you, Gonzalo. Yeah, so I see the chain ID question is answered. Another one is the proof provided for each inference, and does the inference always start from the Cairo VM hosted by Giza, and then it goes to invoke the ape framework to interact with different chains? Correct me if I'm not right. Yeah, I think that's correct. So yeah, the proof is provided for each time you run the inference on the model, and only once that once that proof is generated and verified, only then the action will take place. So like only then the agent is allowed to start taking those on-chain actions and submitting the transactions. And that's what the ape framework is used for. And yeah, under the hood, if I'm not mistaken, Cairo VM is used to generate those. Yeah. Is the proof a point or range? I am not really sure, and I, to be honest, don't understand that question very well. So I will let Gonzalo maybe take it if he can, or ask a follow-up question if he doesn't understand the question as well. Yeah. Thank you, Gonzalo, for all the hard work in the chat. But yeah, I think that's pretty much it. That's all I wanted to show you in this workshop. Do you have any questions related to the code, or maybe want me to show you something else within the code, or explain something? Yeah.
One last thing that I wanted to say is that for those of you that did not participate in the previous workshop, I just wanted to mention once again that there is a dedicated idea form that we would love all of you to fill in before the end of the week. You don't have to do it right now. There's still more workshops to come. Actually, one it's going to be tomorrow's panel, but you can take your time to connect with other hackers and see and exchange ideas on things you would like to build. And then ideally you can submit the form by the end of the week so that the Giza team can then have a look on your idea, what you want to build, and offer the adequate support. As mentioned, we will keep on posting all the relevant links on the Discord in the announcement channel. So you'll probably receive and have been receiving a lot of tags already, but we'll keep on tagging you so that you're aware of where the most important bits are. The recording of this workshop, just as every other one, will be added to the Hacker Pack. We will do these tomorrow morning. We need roughly like 12 hours to go through and prepare all the raw videos and export them and make sure that everything's available. They'll be posted on YouTube and then shared in the Hacker Pack. So feel free to rewatch at your convenience. And yeah, that is mostly it. For tomorrow, just wanted to mention that we are going to have a dedicated partner panel. So all the partners that have come in to provide bounties for the hackathon will come in for a very interesting panel discussion, which will be moderated by the Giza team. So come in and prepare some questions, and hopefully you will enjoy a very interesting conversation. Any words from you, Jakub, to close this off?
There's one more question about adding a dynamic chain ID implementation. So you can make the Giza agents cross-chain, and I think, yes, you can do it already. So remember when we were creating the agent from the CLI, there at no point we were really passing the chain ID to it in any way. So in that case, in that sense, the agent is kind of chain agnostic. What you could do is change this chain ID here in your main Python script. So like based on whatever logic you want, you could like pass a different chain ID into this main action function. Or if you want, you could like pass it probably like a list and like have the agent run through each of the chains that you want to interact with sequentially, or like whatever other logic you see fit for your use case. Yeah, but in principle, I don't think there's anything stopping you from implementing this in a cross-chain way, where like the agent interacts with multiple chains at once using the same agent instance. Another question I see, is there possibility to use LLM agents? Unfortunately not. There's no way to really run verifiable inference on LLMs, just because of how ridiculously large those models are, and yeah, just the state of the art of ZKML is not there to do anything like that. If you wanted, you could design an application that uses an LLM under the hood that figures out how to call the agent that uses verifiable inference itself. But that's kind of like that's not really like ZKML that you're doing in that sense, but it's kind of like like a front end way to interact with the agent, and that's how I would think about it. Are you required to write any ape framework, or is everything required to interact with any chain available in the Python Giza SDK? Yeah, I mean, I don't think there's a way to like completely get rid of ape. So when you look at this and at the code in this Uniswap example, you don't really see it here because I abstracted those functions away. But for example, there's let's say get all user positions function, or like the function that closes the positions, that approves the tokens, that fetches the mint parameters and calculates them. All of those are ape implementations. So in my case, I'm storing them in, I think, LP tools. Sorry, not LP tools. Get tokens. No, not this one. Sorry. Uni helpers. There we go. Sorry. Yeah. So all of those are ape implementations of how to interact with those tokens, with those contracts. Yeah. The good thing with ape is that, well, first, pretty much every EVM compatible chain you will be able to use with ape. If not, creating a plugin for some super exotic chain, if it's EVM compatible, is really simple. If you don't want guidance on that because you want to interact with some interesting new chain, let me know. You can probably hit me up either on our Discord, in the Encode Discord, with in the Gizathon channel, or there's a Telegram with our Giza devs, where I'm also at, so you can pick me through any of those channels, and I can help you out with that. Yeah.
Lovely. And one other thing for those of you that might still have new questions after rewatching a recording or something, as Jakub said, please make sure to post in Discord. Everyone's really active, and your questions will be answered quite fast. So if you have any inquiries, don't be shy and do post. Mahmoud is asking, please, if you can share the ape docs as well.
Yeah, trying to get the link right now.
Right. Anything else to add on your end, Jakub?
No, I think that's it. Thank you for having me. That was fun.
Oh, that's our pleasure. And also, once again, thank you, Gonzalo, for the great support with all the responses. Great. As I said, tomorrow, do tune in. 5 p.m. There's 5 p.m. Central European Time. Invite should be in your calendar. There's going to be a really interesting panel discussion with participants of all the bounty providers for the hackathon. Prepare some questions, come in and enjoy. Thank you, Jakub, for today's session, and I hope everyone in the audience enjoyed it. See you all tomorrow.